Hello and welcome to this talk on following Pareto-Optimal policies in multi-objective planning and reinforcement learning. My name is Diederik Roijers and this is joint work together with these awesome co-authors Willem Rupke, Anne Noé and Roxana Radulescu. In this talk we're going to show you a key issue with Pareto front-based multi-objective RL, namely the Pareto-Optimal policy following problem, and that is that at every time step during policy execution we need to solve a combinatorial optimization problem. And we will show you why in a minute. To this problem we propose two solutions, one based on local search and one based on neural networks. First, let us position this research. We are in a multi-objective MDP, which is that we have an agent that interacts with the world by taking actions. As a result of this action, the state of the environment changes. We get the new state communicated back to the agent together with the rewards that it attained at that time step. And these rewards are vector valued, so we get a reward for every objective. Do we aim to optimize the values? That is to say, we have an expectation over the rewards that we can get at every time step, and these are a discounted sum of rewards, given of course the policy we take. So we have a value vector that corresponds to the value of a policy. We are in the scalarized expected returns optimality setting. That is that the user cares about the utility conferred by this value, so conferred by this expectation. The user utility can be modeled by a utility function, which is then applied to this value vector. We know that this utility function is monotonically increasing in all objectives. That is to say, if we keep all the values for every objective the same, but increase the value of one objective, then at least the utility cannot go down. The problem, of course, is that we don't actually know the utility function, especially not at planning or learning time. This is because we are in what we call a so-called decision support scenario. So the user does not actually articulate the utility function precisely, but instead we need to solve the multi-objective decision problem at planning time or learning time, then show a set of possible alternatives to the user, and then the user will select the most preferred value or policy from that, and then this is executed in the execution phase. And so this execution phase is actually what this research is about. Note that in this covered set we need at least one optimal policy for every possible utility function that the user might have. If we analyze this, we will get to the solution concept that we need for the planning or learning phase, which is we are in a multi-policy scenario, so we're in a decision support scenario. In this paper we assume that policies need to be deterministic, and we have a monotonically increasing but possibly nonlinear utility function. This leads us to that we need a Pareto covered set of deterministic non-stationary policies, and this is what's going to happen in this planning or learning phase. We note that this Pareto covered set is a slightly different set from the Pareto front. If you look at the definition of Pareto front, then it should contain all Pareto-Optimal policies. A Pareto covered set needs only one Pareto-Optimal policy per value vector. However, popular multi-objective planning and MRL algorithms typically produce only the value vectors. And this is very true, for example, for White's 1982 policy value iteration. And which just assumes, okay, if we produce the Pareto covered set, so the values in the Pareto covered set, then we're done. Van Moffaert's Pareto Q-learning does actually contain something of policy execution, but actually restricts the MODeM that we're in to deterministic transition functions. And this is an assumption that we aim to lift in this paper. So if we can actually have multi-objective MDPs with stochastic transition functions. Then still we can use Van Moffaert's Pareto Q-learning in order to learn the Pareto covered sets, and also a reward function, and with a bit of extra effort, the transition function. But then if we have these vectors, then the question of policy execution is actually still wide open. And we're going to show you right now that this is far from trivial. In order to show this, let us start with a simple example. So in this MOMDP, we have a user who has selected the value vector 5, 5 as the desired value vector. So we should aim to follow this vector. So from state 0, this is simple. We can only take one action, and with 0.5, 0.5, we end up in either this state or this state. Now from this state, we can follow either vector 10, 0 or 4, 4 in this first state, or 0, 10 and 4, 4 in this next state. If we are in state S1, 1, we have this Pareto coverage set of 10, 0 and 4, 4. Now what should we do to follow the user selected value function, namely 5, 5? Well, if we pick the closest value to 5, 5, then we pick that here. That would lead us to 4, 4, and it would lead us to 4, 4 here. This is a bit of a problem because actually the value vector 4, 4, which you would get if we would follow this closest value vector strategy, is actually dominated by 5, 5. And we can see that we can actually attain 5, 5 by selecting 10, 0 here and 0, 10 here. So if we just follow the closest vector on subsequent states, then we can get arbitrarily bad results and even Pareto dominated results. So what's the problem? So the closest overall value strategy doesn't work, but we should note that actually the value vector that we were following in the previous state is actually very important to what we should do in the subsequent states. Moreover, the contribution of the value of the state we're currently in to the previously followed value vector is what determines what we should do in this state, right? So in this state, 1, 1, we should pick 10, 0 because the combination of vectors that we could get for all possible subsequent states from this first state actually leads us to that we should take the 10, 0 vector. So the combination of value vectors that constituted the previously followed value vector is actually how we can determine what we should do in the current state. So the vector 5, 5 was built up of 0.5, so the transition probability times 10, 0 plus 0.5 times 0, 10. So if we need to know the entire combination of value vectors that constituted the previously followed vector, then this is of course quite a difficult problem, and this is actually what leads us to this combinatorial optimization problem. Namely, if for the next time step we want to determine how the current value vector is built up from vectors from subsequent states, we need to optimize the following. First, we determine the vectors that are the component that is actually derived from the next states, so that is the transition functions times the vectors that we get in the subsequent states. And to determine this target, we can subtract the expected immediate reward from the value vector that we're currently following and divide by the discount factor. Then we actually formulate the optimization problem. So we have this target and we subtract the weighted vectors for the subsequent states. But actually we need to select these subsequent vectors from the Pareto coverage sets from the next states. This is a combinatorial optimization problem because we have this length here, and this length leads that the target is nonlinear, so we cannot use something nice and simple to solve this problem. Furthermore, we know that the search space of this optimization problem is actually exponential in the number of subsequent states. That is, we have the number of actions that we can take we have the size of the PCSs in the subsequent states. So just take it P, so the maximum. And then those two combined is to the power of the number of subsequent states. Okay, so here we have a combinatorial optimization problem. If we can solve the combinatorial optimization problem, then we can actually perform Pareto-Optimal policy execution. That's to say, we get the selected vector and the initial state, the environment containing also the immediate reward function and the transition functions, and the local Pareto coverage sets for every state action pair. So while the state is not terminal, we can determine the current action to perform by taking the best possible vector from the local Pareto coverage sets. Then execute it. This gives us a reward and the next state. This reward maybe I keep for statistics, but we actually ignore it for the next problem because we need to take the expected reward to determine our target rather than the reward that we actually got. This is because these rewards may also be very stochastic indeed. Then we have this target for the combinatorial optimization problem. We threw it through a selector for the next value vector. So this is solving the pop following problem. This gives us the next vector, and then we set the next state, and then we repeat this process at every time step. So now let us have a look at the solutions for the pop following problem. We propose two, one based on local search and one based on neural networks. So the minimization problem that we have, so this is this equation here at the bottom again, has a nonlinear target because of we need to minimize the length of this vector. It may not be possible to get to 0, and this is also quite an important observation, and this stems from the fact that the planning or learning algorithm doesn't actually produce exact solutions, right? So we don't actually get the exact Pareto coverage sets. And this means that if we would get a 0, we know we have the exact solution. But if we don't get 0, we don't know whether there is a better solution, right? So we don't actually typically know whether we're done or not. In order to solve this, we can use all kinds of heuristic methods. And a key method in the literature is called local search. And local search, we basically start from a random solution. So we take an initiation for, we just pick random vectors for all subsequent states. And then we do minimal, so local improvements. So we replace one of these vectors and see whether the target gets closer to 0 or not. If it does get closer to 0, then we accept the change. If it does not, we reject the change, and we keep on doing this until we run into a local optimum. If we do run into a local optimum, there's two ways to escape it, which we both try out: multi-start and iterated local search. So multi-start is very simple, just do this a bunch of different times from different random start solutions. And iterated local search aims to, once you run into a local optimum, you take a bigger step, so you randomly perturbate the solution and then see whether this helps you escape this local optimum. And again, if it's better, then accept. If it's not better, then reject it. So both these methods we try out in the experiments. We can also take a very different approach based on neural networks. And that is stems from the following observation, that during planning or learning, the vectors that we are obtaining in these Pareto coverage sets are formed using so-called Bellman backups. So in planning, this is a full sweep over all possible subsequent states, and in learning, it's actually one observed subsequent states, but it's still a Bellman backup. And this produces the data, or this can produce the data that we need to solve a supervised learning problem. Namely, we can calculate the target. We have as so the current state, the action we took in the next state, and we also know the vector that has been used to update in the Bellman backup. And so we get the data in the right format to solve the policy execution problem as a supervised learning problem. So when we observe this, then we can predict, using, for example, a neural network, which vector we should follow in this next state. And this is exactly what we do. We train a neural network in order to solve the pop following problem. So now let us compare these two approaches on different MOMDPs. We use random MOMDPs, that is to say, we pick the number of states, actions, objectives, and subsequent states, and then we randomly generate rewards and transition probabilities. For planning, we use the Pareto value iteration algorithm by White in 1982. And we use two different random MOMDPs, one with 10 states, 2 actions, 2 objectives, and 4 subsequent states, which leads us to a whooping total of 19,000 vectors in the local Pareto coverage sets. The second MOMDP we use has 20 states, 3 actions, 2 objectives, and 7 subsequent states. One might argue that this is a larger problem, but actually when we solve it, this led to less than 8,000 vectors in the local Pareto coverage sets combined. So for configuring methods, as we previously mentioned, the neighborhood of the current solution in local search is picking just one different value vector for a subsequent state. And for iterated local search, we use a perturbation probability of 0.3. For the neural networks approach, we use simple MLPs with 3 hidden layers with 16, 8, and 4 nodes using ReLU activation functions. This is important because this is a very basic neural network, right? And we didn't spend any time at all at optimizing the network structure for this pop solving problem. So even though this is a very generic network structure, we will show that it works rather well. We use the MODeM optimizer with a learning rate of 0.0001. In order to measure the quality of the network, we actually use the epsilon metric proposed by Zitzler in 2008. And the reason we use this is because it corresponds to a maximal utility loss. So if we have, we don't know the utility function, right, but we can bound the maximal utility loss for the user. And if you want to see exactly how, then please have a look at this paper. The epsilon metric is defined as follows, namely which epsilon should we add to each objective such that the vector that we actually obtain Pareto dominates the vector that was selected by the user. So you can see that the optimal value for epsilon is 0 because well, we want to have because every epsilon that we add should be positive. Okay, so the epsilon metric results for the first MOMDP with 10 iterations for iterated and multi-start local search actually shows us that local search has not a very good performance by itself, but actually iterated local search and multi-start local search get much better results, and especially multi-start local search, which actually got to the optimal solutions, even though we evaluated this many times, right? Then the pop neural networks actually led us to quite a solid, good solution, but not quite 0. Then for the second MOMDP, the number of iterations still being 10, the local search method actually performed much worse than the neural networks. So, and as you can see, the neural networks actually perform rather consistently across these two different problem sizes. Another important aspect of running these methods is how long they take, right? So if we run them on the first MOMDP, then we see that the local search already takes 5.7 seconds to find to execute a policy. And so policy execution taking 5.6 seconds might not be a problem. But then if we embed it in the multi-start and iterated local search, you get to 15 seconds to execute a policy. And depending on the environment, of course, this might lead to noticeable delays in action execution, right? Okay, in the second MODeM, the local search methods are actually faster, and this might be surprising because it was a bigger MODeM, but actually what determines the runtime of the local search method is not as much the size of the MDP in terms of state and action space, but more in terms of the number of value factors that are in these local PCSs. And we saw for the second MODeM that is actually smaller than the first one. The most noticeable observation here, though, is that these neural networks actually take 0.1 second for the entire policy execution. And so they are 1 or 2 orders of magnitude faster than solving the pop following problem by local search. So actually, while these neural networks perform relatively solid across the 2 different MODems, the runtime for the neural networks during policy execution is a lot lower than for local search. Therefore, this brings us to the conclusions. Firstly, the pop following problem is that during policy execution for a Pareto-Optimal policy, we need to solve a combinatorial optimization problem at every time step. And so this is a difficult problem because we are not home and dry if we just have the Pareto fronts for every state action pair. We propose 2 approaches to solve this pop following problem, one based on local search and one based on neural networks, and we saw that we can get nice solutions with these 2 approaches. So at least the pop following problem is doable. Furthermore, we showed that the neural networks have solid performance across problem sizes and also a low runtime. And therefore, we would advise to use this neural network approach over the local search approach. Thank you for your attention, or as we say in Dutch, dank u voor uw aandacht.